Welcome back. So in the previous lectures, we have seen that given an orbit or a solution to an ordinary differential equation, you can have several possibilities. Possible that the solution will reach a particular point called equilibrium point, which is essentially a point where if it starts there, it will remain there. It can approach some kind of behavior, what we call as limit sets, some kind of limiting behavior where it approaches some periodic solution or some invariant set that we discussed the previous lecture. It's possible, of course, the solution may go unbounded, and in one of those stranger cases, you'll have the you may have strange attractors, right? So what we do now is formalize these notions, provide rigorous definitions, and then see a couple of examples in MATLAB, right? So let's recall that a dynamical system is a triple. The first to provide space and time, and the third one is actually the main ingredient of this dynamical system, which is essentially the function that tells you how a particular dynamical system changes in time and space, right? And of course, we assume that this function S is continuous and it is continuously differentiable in one of the variables. And of course, we have these initial conditions, and then of course it's called semi-group property, where basically if you start somewhere and then go 10 seconds, you can do the same by going 5 seconds and then starting at that particular point go for another 5 seconds. And all this particular dynamical system, the definition is valid for the solutions of ordinary differential equations where we have uniqueness. And of course, if we assume further global Lipschitz continuity, the conditions we have seen, we can actually guarantee solution will exist for all time. And and then that essentially connects this flow that we spoke about, the flow function S and the dynamical system. And for the most of the lectures that we see in the next lectures, we will assume that these conditions are automatically satisfied, and therefore we always have a dynamical system. The only variation that we can think of is perhaps some third variable coming in to put some time varying nature of this system. Other than that, the description of a dynamical system does not get more complicated. Just as a curious remark, basically if one gets rid of this continuity, then things can get quite interesting. I mean, if on the one extreme you have the discrete nature of the time, so that can be dealt with in a relatively simple manner, but you may have actually a hybrid nature where this function S is continuous most of the time and but discontinuous at times and things like that, and how one deals with that kind of dynamical systems is part of hybrid systems theory, which we won't cover in this particular course. But let's move forward, and essentially we can define an orbit. What that means is you're starting from an initial condition. All the points in the space that this particular solution is going to cover, or this particular dynamical system, the flow goes through the entire space, right? Both backward and forward. It allows us to go both backward and forward because of the uniqueness of the solution. And of course, within this orbit, the positive orbit is something that only comes from all the points moving forward, and the negative orbit comes from the other side, right? So these are orbits. That means you start at some initial condition, you move forward, and whatever the space covered by this particular solution is what we call as positive orbit, and then negative side is negative orbit, and combined together is the entire orbit. But we can define something called limit set, right? Now, those of you who are familiar with good analysis will obviously understand it, but I will try to simplify the definition of this particular limit points, right? So the rigorous definition is something like this: P is a positive limit point of this flow S of t comma x if it is an accumulation point of the sequence, some sequence S of t n comma x. So P should essentially be a limit point of some sequence of points on this orbit S of t comma x, specifically positive orbit, but positive limit points come from positive orbits. And suppose if it goes unbounded, so essentially you won't have any positive limit points, but if you have a bounded solution, then it's invariably you'll have some limit points, right? So the set of all such accumulation points is known as positive limit set. It's also called as omega limit set. The omega is the last letter of the Greek alphabet, so that's how people started calling it as omega limit set, and the notation almost seems like a universal notation for this particular set is omega of x, where x denotes the initial condition or for this positive limit set, right? And then we'll talk of a very important result on this omega of x, and then you'll see the importance of this omega of x is cannot be undermined, and some of the best results come out of understanding the nature of this omega of x. So we can of course talk about negative limit points and then negative equivalently the alpha limit sets they're called and denoted by alpha x, but we don't talk too much about negative limit points in this particular course. So that brings us to the next thing that we already spoke about, is something called invariant set. It is a set where if you start within that set, then you don't get out of the set, right? So we call a set as positively invariant if basically if I start in that set and then move forward and then never leave that particular set, that is positive invariant set. On the other hand, it's called negative invariant set if I start somewhere and go back in time and then never leave that set, then it is called negative invariant set. And you can think of invariant set where essentially for any value of time going back and forth, you still remain in the set, right? In the set notation, basically this boils down to S of t comma m is a subset of m, where m is the set that we are talking about. If it is satisfied for all t greater than or equal to 0, then it's called positive and positive invariant set. If it is true for t less than or equal to 0, then it's called negative invariant set. If both of these things are true, one can actually show that S of t comma m is equal to indeed m. I mean, this notation is given for the sake of completeness, but if you understand the intuition behind the fact that if you start in the set in the positive time, if you don't go out, then it's called positive invariant set, and then the other thing is negative invariant set, and finally both of them put together is invariant set. Now this notion of invariant set becomes important, though most of the time we will talk about positive solutions, the solution positive orbits. We can actually use the fact that certain things are true about these omega limit sets and use them to show good asymptotic behavior of your solutions to ordinary differential equations. So some of the standard facts, and more or less straightforward. Perhaps I may give an indication in terms of how this works. So union and intersection of, let's say, positive invariant sets are indeed positive invariant, right? So let's try to understand this how this works, right? So suppose this is M1, which is invariant, and this is M2, right? Now, I mean, it's a fairly trivial thing to say. If it starts in the union, then it remains in the union, obviously. I mean, if it starts in M1, it remains in M1, and M1 is part of union, and therefore you any point in the union is going to be you remain in this thing. So union of two invariant sets are indeed invariant. But more interesting case is basically where you have intersection, right? Now, so if you start somewhere here, we know that we have to remain in M1 because it belongs to M1, but it also belongs to M2. So it has to remain in M2. So that means it has to belong to both M1 and M2. So that means basically the only space that it can go around is basically this intersection. Okay. So in other words, this M1 or M2, in that sense, it's not a minimally invariant set, right? You know, I hope you understand the notion in the sense that you can find a smaller invariant sets within this union of M1 and M2, and that happens to be intersection. And perhaps there are even smaller invariant sets within these two sets, right? So hope that you know, makes it obvious in terms of why this result is true, right? Now, more interesting results and slightly more complicated to understand, rather you have to be, you know, clear about real analysis to understand this. M is invariant, then the closure and boundary and interior are all invariant, right? You know, so for example, so what this is saying, suppose you have this M1, right? Let's say this is an open set for simplicity, so that means the boundary is not included. Then the claim is the closure, that means the set that includes the boundary is also invariant, right? So you know, just the fact that basically you have continuity based, you know, if you remain invariant, all the limit points are going to be on the boundary, and if you start on the boundary also one can show rigorously, you know, it's a little bit more technical than what I'm trying to say here, but one can show that this boundary is also invariant. And more things are true. Suppose M is invariant, and then you know, you have the entire space is D, then D slash M, basically the complement of M, is also invariant, and that tells us even much more about these kinds of results. So then, you know, if closure of M is invariant, and then the open set of the, you know, the interior of the set is invariant, then the boundary will be invariant. So many things are true about these invariant sets, and we will use as and when required, right? Of course, these results are true specifically for invariant sets, but positive invariance and negative invariance are different matter, right? So with these definitions, and we will present one of the most fundamental results that we will keep using it in various cases in the following lectures, right? So the statement is quite straightforward to understand. Most of the time it is quite easy to even prove, except perhaps a couple of parts there, but intuitively they make quite good sense, right? So let some initial condition x be there, and then basically we construct an orbit or a solution around this particular x from an ordinary differential equation, or some flow is going to come from somewhere, and we'll call that as s of t comma x. And the only assumption we will make on this particular flow is it is uniformly bounded. You know, what that means is basically there is a constant that bounds the entire orbit, right? You know, when we say something is bounded, it's possible that for different x we will have a different bound. That's not the case. I mean, for any x basically on this orbit, you know, any point on this orbit, the bound is not dependent on the specific point, right? So then what we can say is if it happens to be uniformly bounded, then the positive limit set or the omega limit set omega x is first non-empty. That means you do have at least one point in that omega limit set. It's going to be compact. That means closed and bounded in standard real spaces. Then it's going to be connected. We will understand what that means, and then finally invariant, right? So let's try to dissect each one of these statements, right? Now, if you have a bounded orbit, that means you have a bunch of points that are bounded, right, on this orbit. So you can find many sequences, infinite sequences in time that move forward, right? So therefore, there is no other possibility, but it will accumulate to some bounded point, right? Imagine, let's say this is your orbit and then it's bounded, right? So eventually somewhere it has to converge to some point. So what we are looking at, this is an example of some orbit that is perfectly bounded. That means, we can bound it some square, let's say. You have no other possibility, but eventually this orbit will have some limit point. So let me use a different color. So in this particular case, the way I depicted, all the points on that circle are the limit points. Now on the other hand, if suppose you have something and it's bounded because it cannot go out, perhaps it keeps touching this thing, and touching once is not enough, but let's say in the limit basically it may be doing something like that, in which case all these points or at least one of the points on the boundary is going to be your limit point, right. So the non-emptiness is quite straightforward, and there are rigorous analysis results that conclude that. Now the more difficult ones are showing that they are closed, that the set itself is closed, and that comes from again continuity of your S of t comma x, and bounded of course is there automatically, right. The most difficult of these things is invariance, and again it specifically uses the properties of your dynamical system, the semi-group property, especially if you start somewhere and then you move forward to some time and then again move forward, then that's the same thing as moving forward twice, once through the entire time, right. And then of course the continuity is there. All these continuity properties and the semi-group property of the dynamical systems or the flow will give us invariance, right. Finally, what is connectedness? So if you have this orbit, you cannot have bunch of, let's say, points that are not connected, right. You cannot have a bunch of isolated equilibrium points, for example, or you cannot have bunch of isolated islands of sets that are disconnected from one another, where there is at least some distance between every pair of points between these two sets, right. So there's a very strict definition of connectedness. Any 2 points of a connected set, you can actually find a line in between, and then line has a very specific way of defining and things like that. Now that's quite interesting, because where does it come from? Again, continuity of your S of t of x. Eventually we'll see that basically when the solution is going to reach some particular set, it cannot just jump and then find another limit set. In the middle, or everything has to be a part of the limit set, right. So why are these important? Because when we look for asymptotic behavior of solutions, we can simply look for solutions that have, definitely there is going to be some set that's non-empty, and then compact and invariant, and then connected. So suppose through some magic we conclude that the positive limit set is in a big set, let's say, but knowing these properties within that big set, what is the biggest positive limit set that has all these features, and then that tells us our solution is going to go there, right. So and then we will use that particular result many times, right. So but the beauty of this particular result is only assumption is boundedness and continuity of S, and then of course the third one that is part of the definition of your dynamical system is the semi-group property, and it just uses fundamental theorems of real analysis. Really, there's nothing that we spoke from the perspective of ordinary differential equation. It so happens that the solution of ODE happens to be a flow that satisfies these three dynamical system properties, but beyond that, any system that comes, any solution that comes from any system. One can I cannot imagine anything but ODE at this time, But as soon as we move out of ODE, suppose the time parameter is changed to discrete, then we can actually talk about discrete systems. But on the other hand, time may remain continuous, and then X, the space part, the solution part becomes discontinuous, then we can talk about hybrid systems. This result is specific for the case where everything is continuous and nice. The generalizations of this result is possible for other discrete times or discontinuous solutions, using again the standard results of real analysis. So in that sense, elevating ourselves to looking at purely just from a flow perspective makes things easier. We don't have to be bothered by what this function that's coming from the ODE is doing, right? So then, where are we going with this, right? So many times we may end up with the asymptotic behavior, the positive limit set being just the equilibrium point, and which is most of the time in controls case, that's what we want. We want to make sure that the omega limit set of a dynamic behavior is ending up with a single equilibrium point. In some cases, we may end up with some kind of periodic nature or a limit cycle that we will define in a second. So, we already spoke about this periodicity earlier, and I'm just putting a rigorous definition. S of t comma x0 is periodic if there exists t such that S of t plus t comma x0 is S of t comma x0, right? And we showed earlier basically, if this is true, then S of t plus 2t also going to be at the same point, and t plus 3t, and so on and so forth. And the minimum value for which this happens is periodic, and then I put a question whether an equilibrium point should be considered as a period and periodic solution or not, and the answer is ambiguous, and then we will take an attitude that equilibrium solution is not a periodic solution because we need to have a positive period, right? And the positive limit set of a periodic solution is the entire periodic orbit. I mean, after all, it keeps going back and forth, and it just keep repeating itself and comes back again and again. So therefore, the positive limit set is going to be the entire periodic orbit. So there are some really interesting theorems that can show lack of periodic orbits. I mean, it eliminates the possibility of periodic orbits. So these are theorems called Bendixson's theorems and Poincare-Bendixson theorems. They are quite interesting, but then I'm not going to some of the details simply because it takes away from what we are trying to do here. But they are there in the literature that I provided earlier, and you should look at those problems and see how to show lack of periodic orbits. So let me show you some examples. Okay, let's hope the internet will work. Yeah, see some activity there. Okay, great. Don't worry too much about whatever here in terms of program. I will explain in a second. So if you're familiar with MATLAB, we can basically write a program to simulate ODEs. Okay, I'll probably make a separate video on some of these examples and then provide it as an additional material. But essentially, you can actually take this nonlinear system and draw the phase portrait, which essentially is the path of each of these solutions. In this particular case, you see a solution starting from some point here and then moving along in how do I put it, 135 degrees or minus 45 degrees angles, so to speak, and it will eventually reach some point. And if you see, this particular phase portrait provides arrows, marks wherever you start. It shows which direction the solution is going to go, right? So in all these cases, wherever you start, you go at 45 degrees and eventually end up with x2 equals 0 line, right? And similarly, if you start above the x-axis, then basically you reach x-axis in a again exactly opposite direction, right? So, and why that happens is basically if you see the dynamics, x1 dot is x2 and x2 dot is also minus x2. So, let me show you the analysis for that and then make some sense of that particular plot, right. So, what we had was x1 dot is equal to x2, x2 dot is minus x2, right. So, first let us understand what are the equilibrium points of this particular system. This simply means x2 is equal to 0. So, any point of the form a comma 0 is equilibrium point. Okay. Now, one of the things that we need to understand is this particular system happens to be bounded, meaning every solution is going to remain bounded. So, how do I see that? One simple thing to do, I guess, is basically, let us say x of x1 of t and x plus x2 of t, okay. Sorry, the derivatives, when you add them, you will get 0, right. What does this tell us? X1 of t plus x2 of t is going to be equal to a constant, and then that constant may be determined from the initial condition, right. So, you can clearly see that this is a number, some number. So, if this is a number, then this is going to remain that number. So, therefore, it is going to remain in that particular line, right. And one can show on the other hand just x2 dot, you can clearly see the solution to this is basically e raised to minus t x0 and x2 is 0. So, that means this is a bounded this thing. So, if this is x of 2 is bounded, and that actually shows that x of 2 is going to go to 0, right. So, if x of 2 is going to go to 0 and x1 is going to therefore remain this entire constant minus that x of 2 to 0. So, x1 of t is going to go to this particular number. So, asymptotically we can see that all of them are going to end up with the equilibrium point on the x axis, right. So, in this particular case, the omega limit set happens to be one of the equilibrium points, okay. So, once you are there, it is going to remain there, and then of course, each of those things are equilibrium points. So, they are indeed invariant. Now, let us consider a slightly more standard example. Unfortunately, the MATLAB is not working in my case, but if I do some kind of phase portrait, we will see that basically any point you start, it will actually go around, and then it is going to become a periodic orbit. And why is that? Because I can think of this as basically x1 double dot as x2 dot, x2 dot, which of course is minus x1. So, this is essentially x1 dot plus x1 is equal to 0, and we can see a similar equation for x2, and this tells us the solution to this is sine or cosine, right. I mean, that is by looking at the solution. So, and then the fact that x2 dot is minus x1, x1 dot is x2, and then if x1 happens to be sine, then x2 will be cosine, and or they complement each other, and then you will end up with a circle, right. But of course, this I showed through the solution, but there is a even cooler way of doing it. So, I am going to basically consider this function, okay, let us call it as, I don't know, v of t or something like that, and then take the derivative of v, and I will get 2x1 x1 dot plus 2x2 x2 dot, and by substituting x1 dot is x2 and then x2 dot is minus x1, we will end up with 0. So, again we have this nice interesting condition that v of t is equal to constant, and then that constant is going to come from V of 0 because we know the initial condition. I mean, at least we typically assume that we have an initial condition, and that of course V of t is x1 square plus x2 square is constant, which of course we all know that, and then that constant happens to be positive. When you substitute the initial condition, you're going to get positive, and then that shows that this solution is going to be a circle. And then not only the solution is going to be circle, this also shows invariance of that particular circle, right. So you have every point will be a periodic orbit, therefore it's going to be the entire orbit, and then that entire orbit is going to be invariant, and so on and so to speak, right. So of course the only trivial point is the origin, where things will start there and will remain there, but everywhere else you will get bunch of circles, right. So you have many such examples. Let me try once more this MATLAB to see at least if we can run some other example. So I mean, even other systems seem to have worked eventually, but let's see. So this is the so-called famous van der Pol system. The specific dynamics can be seen, can be searched on Google, but essentially you will have a behavior that's quite interesting. It's possible only in nonlinear systems, where you start off somewhere and you always end up with this the thing that you see here, shaped like a rectangle that's slightly twisted. So you the limit points of any solution is going to be that particular rectangular shape, right, whether you start inside or outside, except the origin, which happens to be an equilibrium point. You have for everything else, basically you end up with this particular van der Pol oscillator, it is called, right. So through our invariant set theorem, what we can actually conclude that this particular limit cycle, if you start within that, it's going to be there. I mean, this is going to be an invariant set. Clearly it's compact, it's connected, you don't have disconnected components of this particular set. I mean, it's a single set. If you start there somewhere, you can actually traverse the entire set without lifting your pen, so to speak. So it's invariant, it's non-empty clearly, and it's compact and connected, right. So these are the various things that one can speak about, and the second system also, you have this crazy looking behavior where you have bunch of equilibrium points, and then it will tell you a little bit different kind of behavior. In all these cases, again, the same story, which is essentially saying you'll have if you have bounded bounded orbits, then you'll have either equilibrium points at the end of time. The asymptotic behavior is going to be reaching some equilibrium point or some kind of limit set, and in the worst case you'll have some chaotic behavior, right. So only other possibility is basically the solutions are going to go unbounded. In the context of controls, we don't want anything going unbounded, we want perfectly bounded, and most probably in most of the cases we'll have a target solution to reach, and that's trying to reach an equilibrium point. Suppose the natural behavior of, say, something like a van der Pol system is its limit cycle. Can we actually put a feedback control so that limit cycle behavior is going to be modified to a point to a case where we have equilibrium points? So one of the things that I haven't touched upon is basically we seem to be obsessed about the origin being the equilibrium point, but it's not necessary. It's just that in a coordinate system, you can pick anything to be an origin. You can just shift the entire coordinates to that particular point. So anything that we desire to be the final target of our control problem, we call that origin, and therefore we develop the theory with respect to such an origin and nothing else. So therefore we will keep on using zero origin as the most of the time only equilibrium point, but if we have multiple equilibrium points, still typically we assume that there is an equilibrium point at 0, right. So that brings to the end of this particular lecture, which spoke about asymptotic behavior of solutions, and in a way we have seen rich dynamic behavior that's possible, whether the solutions are bounded or unbounded. But then we'll start looking at some behavior that is desirable in a control system, and then we'll start with definitions of stability, different types of stability, and specifically we are interested in the notion that was introduced by one of the greatest systems theorist or person who understood dynamical systems very well, named Lyapunov. And we will start the next set of lectures on Lyapunov stability. Thank you.